Good morning, good afternoon, and good evening to all our customers joining us across the globe. Hello, everyone. My name is Lokesh Sharra. I'm one of the managers for the Arista Technical Services team, and I would like to welcome each and every one of you to this webinar hosted by the Arista TAC team. And before we start, thank you all for the overwhelming response to the Arista TAC initiative. A little bit about this initiative in general for the customers who are joining us for the first time. With these webinar sessions, our aim is to work on the knowledge sharing with our customers and cover topics in depth which are most useful and applicable to all our customers. We started this effort in 2022 and we covered topics like switch health check, upgrades, and maintenance planning, which were kind of very basic. And now continuing in 2023, we are focusing on more technical topics like layer 2 and layer 3 routing and more. Recording of all our previous sessions, including the presentation material, is available on our community pages if you would like to review it. In the 2023 series, Q1 webinars, we were focusing a lot on the debugging typical layer 2 and layer 3 setup, where we covered a lot of good use cases and commands which are helpful to debug such environments. And now in Q2, with this session, we are going to focus on VxLAN setup, which was actually a demand from our customers. We definitely take that feedback very seriously, and now VxLAN is our topic for Q2. So in this session, we are going to cover common tools and tricks that are available at our disposal in EOS CLI and Cloud Vision, which can make debugging any VxLAN environment easier. So today we are going to do a deep dive into the bridging setup, and in our upcoming sessions in May and June, we'll focus more on VxLAN routing and also on the complex VxLAN environment. So for today's session, we actually created a lab topology based on our customer interactions, and we'll be navigating through this topology and highlighting the debugging approach. We actually did send this topology proactively to our registered customers on 24th of April, repeat on 25th as well. Our speakers will also be highlighting this topology in between the debug scenarios, but it will be a good idea to take a snapshot of this topology and keep it up on your screen for reference. We have a PDF download link available in the QA sections, which our panelists are putting up now. So please download it and keep it handy during the course of presentation. A little bit about the webinar schedule in 2023. We have 3 sessions planned in Q2, which are going to focus on VxLAN. And then after that, we have our fall series, which will start in September for 3 more sessions. And then we are going to cover EVPN in those 3 sessions. And we are going to do a wrap for the year in November 23. Today, we have 2 of our best engineers with us who will be taking us through the today's sessions. We have Madhukar Sharma, who will take us through the CLI component, and then we have Arvind Mohan, who will run with the Cloud Vision side of presentation. Again, these sessions will be recorded, and it'll be made available on the Arista Community Central if you'd like to have access to these sessions and for future purposes. Along with the presenters, we also have our technical leads as part of the panel who can help answer any questions you may have during the presentation. We highly recommend you use the Q&A manager to ask any questions what you may have during the course of this presentation from our panelists. We'll try our best to get to all the questions, but in case we are not able to get to all during the stipulated time, we'll definitely follow up via the email after the presentation. And if there are any unforced errors, we apologize in advance, and we'll be looking out for the feedback to make improvements. So without taking any further time, I'll hand it off to Madhukar for taking you through the CLI part. Madhukar, take it away.
Thank you, Lokesh. Good morning, good afternoon, and good evening, everyone. My name is Madhukar Sharma, and I'm one of the technical solutions engineer here at Arista Networks. In today's webinar, I'll be one of your key presenters on this session on debugging traffic flow through the VxLAN fabric. And before we jump into the deep, the troubleshooting part, let's quickly discuss the scope of this session. So as discussed by Lokesh, in this webinar, we will be discussing the useful strategies to debug VxLAN Layer 2 environment by demonstrating some of the best practices by using the EOS commands, which will help us troubleshoot and isolate issues in a VxLAN fabric. Later in the session, my colleague Arvind will discuss a few useful techniques and show you some cool tricks on how Cloud Vision, which is one of our popular products, can be used to troubleshoot a VxLAN Layer 2 environment. Now with that, let's quickly take a look at the topology diagram, for which the link must have been shared on the Q&A section. So I definitely recommend you guys to download the topology and keep it handy so that you can go back, map out the details and reference to the addresses or anything that we are troubleshooting or having a look at the CLI. Now, as we can see here, this is a traditional spine and leaf architecture, wherein the leaf switches are acting as two set of VTEPs, which are in MLAG. So we have VTEP 1A and 1B, which are one set of VTEP, providing logical redundancy to the VTEP IP 2.2.2.2. And we have the other set of VTEPs, VTEP 2A and VTEP 2B, having or providing logical redundancy to the VTEP IP 1.1.1.1. Along with that, we have two hosts, which are dual home to these set of VTEPs. Host 1, which is behind VTEP 1A and 1B, has an IP address of 10.10.10.8 and has a MAC address ending in with 4A89. On the other side, we have a host 2, which has an IP address of 10.10.10.9 and has a MAC address ending in with C361. Lastly, we have the spine devices, which act as an interconnect between these VTEPs and provide a layer 3 ECMP links between them. Now, along with the topology diagram, we have also mentioned the various platform devices, which are a part of our product portfolio, which we will be using as a part to reference these devices. And just to keep the topology uniform, we are running all switches on the EOS code version 4.28.3, which is a maintenance release. With that, let's go ahead and look at our first problem statement that we'll be discussing. So, the first problem statement or the issue reported by our customer is that they are observing intermittent connectivity issues between the host 1 and the host 2. Now, to gather more details about this issue, we just followed a baseline approach of asking more questions. And we observed that, this is a new deployed setup, and the customer is suspecting intermittent failure in the application traffic between the two host machines. To chalk out the flow or, to reference out or make our troubleshooting a bit easy, we took a sample flow using customer's assistance, and we will be using the source as the host 1, which will be 10.10.10.8, and the destination IP being the 10.10.10.9, which is the host 2's IP. Now with that, let's quickly look at the CLI troubleshooting part and see what are the best practices and what are the useful EOS commands we can use to troubleshoot such issues. For this, I'm going to make use of a pre-recorded video, so please follow along. So we start off with our first test by initiating an ICMP echo request from host 1 towards the host 2. And for this test, we're going to keep the interval as 0.5 seconds to keep it a bit aggressive. And to keep a cap on the number of packets being sent, I'm going to use the -c flag and restrict the number of packets being sent to 10. Now, upon running the ping command, I can see that there is a failure in the stream of communication. And as discussed in one of the previous webinars, the Arista switches use flow-based ECMP hashing that by default takes into consideration the 5-tuple input, which is the source and destination IP, source and destination port, and protocol ID to decide what particular path a particular stream would be taking in an ECMP environment. So this 100% packet loss that we see here is an indication that the path taken by the ICMP stream of communication has some fault, or if there is something wrong in that path taken by it. Now, as an alternate test, let's use the curl command, which is an Linux utility, which is used for injecting some form of application traffic between the two end hosts. And in this case, we are injecting the TCP stream of traffic using the telnet to use some level of entropy in our test traffic. And for that, we're going to use an arbitrary port number 50,001. For this test, we are going to run multiple iterations of the curl command to confirm whether or not this is a complete failure or this is, an intermittent failure as described by the customer. Now, upon running the curl command multiple times, we are able to see that for the majority of the cases, we are observing that the TCP connection or a bidirectional stream of communication is failing to form. But in one of our recent iterations, we see that the TCP connection between the two end hosts was forming. However, we see a connection refused error state being passed on, which only means that the port 50001 on the remote device is not in an open or a listening state. And as soon as that happens, the TCP connection is closed down. Now, as we can see that there is an intermittent failure, let's move on to our next set of devices in the uplink and have a look at the uplink status by running the show interface port channel command. And we see that the port channel 100 is up and connected with the local and the peer interface members rightly bundled into it. Looking at the input counters, we see that the input packet counters on both these ends are non-zero, which means that the port channel was receiving traffic previously as well. Looking at the input counter discards and the output discards on both sides of VTEPs, we see that the counter values of these section is 0, which means that on a high level, our uplink is running fine. With that, now that we have confirmed that the uplink is running fine and this is an intermittent issue, let's try to trace or map the path taken by the packet from the host towards the VTEPs. And for that, we're going to run a continuous stream of ICMP test or ICMP stream of communication by using the ping command and keep the size of the packets being sent as 300 bytes. To trace the path of the packet taken by the host towards the VTEP, we're going to run the show interface counters pin output in conjunction with the watchdiff command so that we can just reference out the counter changes in real time. Now, after running the show interface counters bin output under watchdiff on both sides, we do see that on VTEP 1B, the counter values are not incrementing. But when we look at the VTEP 1A, I see the counter values increasing for the packet byte range 256 to 511 bytes. Now, this packet range coincides with our size of the test stream of traffic that we are sending across from the host. And this gives us some level of confirmation that the traffic from the host is getting hashed towards the VTEP 1A. Now, before we look into we get some visibility into the flow of traffic being received from the host towards the VTEP, it would be a good idea to look at the layer 2 tables across these VTEPs and see what are the details in it. To do that, we're going to run the show MAC address table output, and we're going to go filter out the MAC addresses exclusively for VLAN 10 because this is a bridging flow that we are interested in. Looking at the MAC address table output on both ends, I see that I have a couple of MAC addresses on the on VTEP 1B. The first MAC address that I see here in this case points to the host 2's MAC address, as you would have seen in the topology diagram as well. And the MAC address of host 2 is being learned behind the VTI or the VX1 interface. Looking at the other MAC addresses being learned in VLAN 10, I see that is corresponding to that of the host 1 and is rightly learned behind the local MLAC port channel 100. So now, since these VTEPs are in MLAC, it is a good way to check which particular device will be receiving the traffic. And once we confirm that, we know that in a MLAC setup, the traffic will be getting hashed towards one of the MLAC peer, and the other MLAC peer will be learning those set of MAC addresses over the peer link. Now, this process is done over by the MAC synchronization, and this has been discussed in one of our previous webinars that happened last year. But if you haven't looked at it, I would definitely go ahead, recommend to see that on our YouTube playlist and look at the other contents or other videos that we have created for you. Now, to confirm, what particular MAC address is being learned behind the peer link, and which particular VTEP is acting as a MAC owner for these particular MAC addresses, we are going to run the show MAC address table MLAC peer output. And when we run that, we see that the VTEP 1B is learning both the set of MAC addresses over the peer link. Now, what information does this output gives us? It gives us a confirmation that the VTEP 1A is acting as the MAC owner for these set of MAC addresses, which we are learning on the VLAN 10. Well, now that we have traced the path, we looked at which is the MAC owner, and we've confirmed that this is an intermittent failure. Let's gather some form of visibility into the flow of traffic being received from the host towards these VTEPs. And we're going to do that by using the show monitor session or mirror to CPU. Now, this process or this feature has already been discussed in our previous webinars as well. And for this case, we have already configured a few set of monitor sessions that we'll be using or referencing out to look at this packet stream on our CLI screen. In this case, I see that I have already created a monitor session named test. Now, this monitor session test, if I look at it, it is punting traffic from port channel 100 in both direction towards the CPU. And this monitor session is being referenced under the mirror interface mirror 0. Now, to look at the traffic or to display the traffic being received from the host on these VTEPs, I'm going to run the CLI command bash TCP dump, and I'm going to inject the traffic received from mirror 0. And I'm going to use some baseline filters that of VLAN 10 is the communication I'm interested in, and using the host filter pointing to the IP address that of host 2, which is 10.10.10.9. Now, to not overwhelm the number of packet captures we see on the CLI screen, we are going to restrict it by using the -c flag and only display the first 10 packets that are recorded by the bash TCP dump command. Now, upon running the bash TCP dump command, we again get a reconfirmation of what we confirmed earlier, that the traffic from the host is getting hashed towards the VTEP 1A. And we see that there is an entire stream of communication being received for the 10 packets. Now, let's look at the packet details of this particular traffic being received from the host perspective. Looking at the source MAC of the stream of communication being received, we see that this MAC address is pointing towards that of host 1, which is locally connected to the VTEP 1A and 1B. Now, looking at the other MAC address, I'll definitely recommend you guys to, again, reference to the topology diagram that you have on your other screen. And we see that the destination MAC address, which is ending with C361, is pointing towards the host 2's MAC address, which is remotely connected to the other set of VTEPs. Now, since this host is connected to a trunk link, I do see the VLAN tag present in the ICMP stream of communication, or the packet received from the host. And since we are using ICMP as a test traffic, I do see the protocol ID being populated as ICMP, with the source IP being that of host 1 and the destination IP being that of host 2. With that, we get some confirmation that the traffic being received from the host is correctly sent across, and the VTEP is learning or receiving that in a right manner. Now, at this point, it would be a good point to check the VTI status, which is the VX1. But before we look into it, or would we discuss the other details in VTI, let's quickly discuss a few technical jargons that we are discussing or are relevant in the VxLAN domain. Now, VTI, or the VxLAN tunnel interface, is basically a switch port which is linked to a UDP socket. And the use of VTI is that any traffic which is sent from the bridging domain towards the VTI will be responsible for encapsulating that traffic with the correct VNI labels and the outer overlay header details, and sent across that particular packet through the VxLAN fabric. And vice versa, any traffic received in by the VxLAN fabric onto the VTI will be responsible for decapsulating that particular traffic and sending it across to the bridging domain. Now, since we have two devices which are working as a logical VTEP, which is VTEP 1A and VTEP 1B, it's a good point to see what is a VTEP. Now, VTEP is basically a device which is capable of performing VxLAN operation and has a presence of at least one VTI on it. In this case, we do see that the VTEP 1A is acting as one of the other VTEPs. So let's quickly go ahead and verify the other details present in the VTI as well. Now, upon running the show interface VX1 output, I can see here that my VTI, which is the VxLAN interface 1, is up and connected. And looking at the other details, I see that my source interface, which is acting as the referencing to the loopback 0, is taking up the VTEP IP that mentioned in the loopback 0 or the loopback 0's IP, which is 2.2.2.2. And looking at the other details on it, I am going to see, what is the flood list source for it. And seeing the flood list source for it, it is mentioned as, it's CLI, which means that I have manually configured the static flood list, which is going to be a part of our next checks as well. What this information says that, any remote MAC address learned over the VTI is going to be learned via the data plane. And the other details, or looking at the other details on this VTI, I see that there is a static VLAN to VNI mapping, which is being configured. Now, this is a very important information, either because the static VLAN to VNI mapping gives us some form of visibility on what VLANs are extended over the VxLAN domain. And in this case, I see that we have extended a single VLAN, which is VLAN 10, and we're extending that with a VNI label of 1000. So any traffic which is received from the bridging domain and comes onto the VTI with a VLAN labeled 10 is going to go out across into the VxLAN fabric with a VNI label of 1000. Now, the other subset or the other check or other things mentioned in our interface VX1 output is the hidden replication flood VTEP list, which is basically the flood list which we had configured manually. And this flood list comes into action whenever we receive any form of bump traffic on these set of VTEPs. These VTEPs, upon receiving any bump traffic, which is the broadcast, unknown unicast, and multicast traffic, is going to create multiple copies of the VxLAN encapsulated packet and IP unicast that using the underlay connectivity. Now, another table which comes in very handy when we are discussing the VxLAN troubleshooting, or when we are discussing any VxLAN flow, is the VxLAN address table. But before we discuss that, let's quickly verify the other VTI details on the other VTEP as well. We see that the VTI is up and connected, the source interface is loopback 0, and the IP address is configured same as that of VTEP 1A, and the static VLAN to VNI mapping at the head and replication list is identical to that of the VTEP 1A. Now, looking at the VxLAN address table, what we were discussing, this particular address table works in conjunction with the MAC address table output that we see or we observed earlier. And what the VxLAN address table does, it gives us the information of any remote MAC which is learned behind the VTEP, and gives us that information that behind what VTEP IP is that remote MAC learned. This helps the VTI in making those forwarding decisions. So let's say I receive any traffic for the remote MAC learned over the VTI will be able to decide what VTEP IP do I need to send that particular packet. Now, looking at the details of this VxLAN address table output, I see that the MAC address of host 2 is being correctly learned behind the VTEP IP 1.1.1.1, and this is being learned behind the VTI, which is the VX1 interface as well. Well, now that we know the trace of the packet from the host towards the VTEP, we know the VTI details, we know behind which VTEP IP the particular remote MAC is learned. It's a good time to check now the underlay connectivity or the VTEP to VTEP connectivity between these two set of VTEPs that we are discussing. Now, to do that, we are going to check, or we are going to see if we have valid routes for the remote VTEP IP that we are discussing, which is 1.1.1.1. And we're going to run the show IP route command and look at the valid routes for these remote VTEP IPs. Now, upon running the show IP route command, I do see that I have two valid routes for these set of VTEPs, or this set of remote VTEP that I see here. And to check the connectivity between the two VTEPs, I'm going to make use of the ping command, and I'm going to source my ICMP packets using the source loopback as 0, which is the VTI interface or the source loopback interface used for the VTI. Now, since these set of VTEPs are in MLAG, the ICMP messages sent by either one of the either one of the packets or either one of the devices, the responses may get hashed towards the other set of VTEPs or the other MLAG peer, because they are using or they own the same logical VTEP IP which is being used. Now, upon running the ping command from both the set of VTEPs, I do see that the traffic or, the VTEP 1B does not get any responses back. But when I run the ICMP or the ping command from VTEP 1A, I do see that the ping responses are coming back onto VTEP wake correctly. That gives us a confirmation that, the traffic is, or, we have the underlay connectivity between the two set of VTEPs. And now would be a good point to get some visibility into the flow of traffic being exchanged between the two set of VTEPs or in the VxLAN fabric in general. To do that, we have already created a monitor session named test_overlay, and it's going to, punt the traffic received on the uplinks towards the spine all the way to CPU, and is getting referenced under the mirror1 interface. Now, to display the VxLAN specific traffic that we want to see, we need to use a specific filters. So we can use the UDP port number that is assigned or socketed to the the VTI. And to do that, we are going to run the show run interface VX1 output, and we see that the VTI is mapped to the UDP socket 4789. Now let's put the filters and just use the -c flag to restrict the number of packets being displayed on the CLI screen. And when we run the bash CLI command bash TCP dump, we do see that the traffic is, we do see some form of overlay traffic on both the set of VTEPs. So let us, just let the TCP dump converge and then look at the details of the traffics being exchanged between the two VTEPs. On the VTEP 1A, let's reference out one particular packet and look at the details of, the overlay and the underlay, packets that are being exchanged on this stream of communication. So we can definitely see as a part of the, the outer header or the VxLAN overlay header, the source IP is that of the VTEP IP of the local VTEPs, VTEP 1A and 1B, having a source port which is, calculated impromptu. And it has a destination IP towards the remote VTEP IP 1.1.1.1, and the destination port is a de facto VxLAN port which is used, which is the 4789. Along with that, as discussed earlier, under the other important information in the overlay header, I do see that there is a VNI label of 1000, and then the underlay or the inner packet details start. Looking at the inner packet details, we verify that it's the same as what we saw earlier, with the source MAC being that of host 1, the destination MAC being that of host 2, and the protocol of the test traffic as sent by the host 1 is that of ICMP. And when we look at the source and destination IP of the inner packet, we see that it's rightly configured as the host 1's IP and the destination IP being the host 2's IP. Now, since this is an ICMP echo request, I see that this sequence number packet is referenced with 666. So let's look at, or let's identify if we can find the return packet with the same sequence number. Now we're able to see that there is a same sequence number reply packet response received on these set of VTEPs from the, the remote VTEP IP. As the source IP for this return packet is that of the remote VTEP IP 1.1.1. And we do see that, the destination IP for this VxLAN encapsulated packet is destined towards our local VTEP IP, which is 2.2.2.2. But there is one thing that I see here, which is a bit different from our send traffic. I do see that the VNI label of the return packet that is sent to us by the remote VTEP has a VNI label of 1001. Whereas the VNI label of the sent traffic or the packet sent by us locally was having a VNI label of 1000. Yeah, but let's first also, verify the other details and see if there is any other discrepancy or any other, changes that I see in the return traffic as well. I do see that, the source and destination MAC are rightly populated in the inner packet details. The protocol is ICMP, and the source and destination IP is correctly configured. Now, at this point, it would be good to check the VTEP status or look at the layer 2 MAC address table details on the other remote set of VTEPs. And let's do that by running the show MAC address table output on the VTEP 2A and VTEP 2B and filter out only the details for VLAN 10. We see here that, there are two MAC addresses being populated, and we see the MAC address of the host 1 and host 2 present in the MAC address table. Now, when we look at the VTI status on the VTEP 2A and VTEP 2B, we're going to check what and verify what are the other details and what is the status of the VTI. And we see that the VTI on VTEP 2A and 2B, they're both up and connected. Both are using a source interface as loopback 0 with having an active IP address of 1.1.1, which is rightly configured on both ends. But when we look at the static VLAN to VNI mapping on both these set of VTEPs, we do see that the VTEP 2B has a VxLAN to VNI mapping for VLAN 10 that of 1001, but for the VLAN 10, the static VLAN to VNI mapping on VTEP 2A is 1000. Now, this is definitely some form of discrepancy that we also observed in the packet stream or the stream of traffic we recorded across the VxLAN fabric on the set of VTEP 1A and 1B. And if there are such config errors, or if there is some form of discrepancy across two VTEPs, we also have a command called show VxLAN config sanity, which acts as a VxLAN config checker. And to give you more context on this, this command is a platform independent command, and it gives you the visibility or information on any misconfigs that may have happened on the VTEPs, or if there is any sort of platform dependency check which is failing on the set of VTEPs. And along with that, it also gives you the details about any discrepancy or anything that may be causing a suboptimal behavior in your VxLAN fabric due to this particular VTEP. Now, this command in general, as per my recommendation, is one of our hidden gems in the EOS ecosystem, and it gives you, all sort of baseline checks that needs to be done. Now, looking at the show VxLAN config sanity output on both the set of VTEPs, I do see that the VTEP 2A is generating a MBLAC configuration check failure, mentioning that the peer VLAN to VNI mapping is failing. To gather more visibility or checking more details on it, we're going to run the show MBLAC config sanity, which again, this command has been discussed in one of our previous webinar. But looking at the MBLAC config sanity output, I do see that there are some inconsistencies being identified, and I do see that the VLAN 10 VLAN to VNI mapping has a local value of 1000, but the peer value configured is that pointing towards 1001, which we also identified using the show interface VX1 output. Now, since these two set of VTEPs are in MBLAC, they are supposed to have the same VLAN to VNI mapping, and this kind of explains why we were observing this intermittent failure whenever the traffic was sometimes getting hashed towards either one of the VTEPs. So for context, whenever the return traffic from host 2 was getting hashed towards the VTEP 2A, it had the return traffic VNI label of 1000. Whereas whenever the traffic from the host 2 was getting hashed towards the VTEP 2B, I saw that the return traffic had a VLAN to VNI label of 1001. And because of that, my remote VTEPs, or the VTEPs that we were troubleshooting earlier, the VTEP 1A and 1B, were dropping that packet upon receiving it on the VTI. So now let's go ahead and correct the VLAN to VNI mapping on this particular VTEP, which is the VTEP 2B. And we'll go into the VTI config mode, and we're going to make these changes. And let's verify the VTI status again and see if the changes are being reflected well. Now we do see that the static VLAN to VNI mapping for this particular VLAN has changed. And let's look at what are the changes being observed in our test traffic. We do see that the VLAN or the test traffic that we were sending earlier started to see the ICMP replies coming back onto the host. And before we consume or we confirm that the issue has stopped, let's go ahead and induce some level of entropy by running some iterations of the curl command. And again, we're going to use the telnet to induce some TCP traffic between the two end hosts using the same arbitrary port number. Let's run a couple of more iterations of the curl command to see if there is any failure. And I do see that there is a bidirectional stream of traffic which was correctly formed, or is being formed between the two end hosts. So we kind of identified why we were seeing those intermittent failures. But before we jump on to the other problem statement, let's quickly go back to a slide deck and discuss the the summary, or map out the details and the approach we discussed while troubleshooting this particular issue. So firstly, we saw that the communication was intermittently failing between the two end hosts, and we confirmed that by using the curl command, by running or injecting some TCP stream of traffic between the two end hosts. After that, we confirmed the uplink status on both these set of VTEPs. But firstly, we confirmed it on VTEP 1A and VTEP 1B. We saw that, the MAC address table output, or, the MAC addresses on these locally connected VTEPs from the host one's perspective was rightly populated. And we traced the path of the traffic taken by the host one towards the VTEP 1A or 1B. And we saw that the traffic from the host was getting, hashed towards the VTEP 1A. We also verified the VTI details on these set of VTEPs and confirmed the underlay connectivity on, the VTEP 1A and 1B. And after doing that, we got some visibility into the flow of or the overlay traffic between the two set of VTEPs. And we were able to see there was some form of discrepancy in the return traffic being received from the remote VTEPs, which was VTEP 2A and 2B. To verify the other details, we went on to check on, the VTI status and identified some level of discrepancies between the VTEP 2A and 2B. And we saw that there was a VLAN to VNI mismatch between the VTEP 2A and 2B for the VLAN 10, which was being extended across the VxLAN fabric. We were able to identify that using the VxLAN checker as well. And when we corrected the VLAN to VNI mapping on these two set of VTEPs, we were able to see that the traffic was flowing correctly and there was no failure observed between the two end hosts anymore. I've also listed out the various commands that we used during our troubleshooting so that you can reference it out after the webinar. And with that, let's move on to our next problem statement as mentioned by the customer. For this particular problem statement, the issue reported is that MAC addresses are flapping, or MAC address flaps are observed on the VTI. And to gather more details on it, we asked about some baseline questions to the customer. And again, he mentioned that this is a newly deployed setup. Now, since this is a newly deployed setup, we couldn't get much details or a complete network diagram, which would give us the end-to-end connectivity. So we'll try to just map out the basic details here. So we have the VTEP 1A and VTEP 1B, which are our one set of local VTEPs, and we are having a sample flow that we'll be troubleshooting it with with the host one having an IP address of 10.10.10.8 and the host 2's IP, which is 10.10.10.9. The host one's is dual homed and connected to this logical set of VTEP 1A and VTEP 1B, and we'll be sending out, or we'll check by using some form of test traffic to see what are the increments being observed on the MAC address table, and what are the other symptoms and observations when we try to troubleshoot this issue. Now, with that, let's go ahead and deep dive into our troubleshooting on the CLI, and let's look at the other details on it. Now, as a first step, I am going to check the MAC address table output on the locally connected set of VTEPs, which is the VTEP 1A and VTEP 1B. And upon running the show MAC address table output and filtering out the MAC addresses for VLAN 10, I do see that we are seeing a couple of MAC addresses. The first one being that of the remote host, which is host 2's MAC address, which is being learned over the VTI, has a MAC move counter value of 39. And the last MAC move that happened was 22 minutes ago. Looking at the same details or verifying the same output on the other set of VTEP or other VTEP, which is VTEP 1B, I do see that I'm seeing a similar behavior wherein the remote MAC, which is that corresponding to the host 2's MAC address, is being learned behind the VTI. And I do see the MAC moves counter to be similar to that being observed on the VTEP 1A. Now, as discussed in previous, the VxLAN address table, which works in conjunction with the MAC address table, is a good step to check, or a good output to check whenever we are troubleshooting a VxLAN flow. And upon running the show VxLAN address table output on both the set of VTEPs, we do see that in the VLAN 10, I am receiving the MAC address, or the MAC address of the host 2 is being learned to behind the VTI, which is the VX1 interface. And the VTEP IP behind which this MAC address is being learned currently is that pointing to 1.1.1.1. And the MAC moves counter, as we discussed, is similar to the value that being mentioned in the MAC address table output. But just to induce some test traffic and see if there are any changes, we're going to again make use of curl command to have some level of entropy in our test traffic. And we're going to inject TCP stream of traffic between the two end hosts using the telnet command. And we're going to use an arbitrary port number again. Now, as we can see, the TCP connection seems to be formed, but the connection refuse status that we see here is only an indication that the remote host does not have 50,001 port in a listening state. Now, upon running the curl command a couple of more times, let's quickly go ahead and also check what are the output, or if there are any changes in the VxLAN address table output for this case. Now, seeing that, our MAC moves counter incremented, and we also see that the remote VTEP IP behind which the remote MAC was being learned has changed again. At this step, it will be good to check, the VxLAN address table under the watch diff so that we are able to see any real, changes happening in the VxLAN address table real time. And while doing or, verifying that, we are going to continue sending our test stream of traffic by running multiple iterations of the curl command from our host perspective. Now, upon running the curl command multiple times, I do see that the VTEP IP behind which the remote MAC was learned has changed again, and we have an increment in our MAC moves counter. And when we run the couple of iterations of the curl command again, we do see that let's see if there are changes, and we do see that there are the changes in the VTEP IP behind which the remote MAC was being learned, and the MAC moves counter has incremented by 1 again. So this gives us a confirmation that the MAC address, which is being learned remotely over the VTI on the VTEP 1A and 1B, is flapping between two set of VTEP IPs, which is 1.1.1.1 and the other VTEP IP being 1.1.1.2. Now, this particular output or this particular information can also be identified by making use of the event monitor, which we have discussed in one of our previous webinars that happened late last year. And to give you some context on what the event monitor does, it's basically a data structure which makes use of the table outputs that are being processed or being populated at the back end of our code whenever there is traffic being received on these switches. So the show event monitor or the event monitor fetches the data from that particular tables or those outputs, and it presents it in a user readable format on the CLI screen. In this case, we'll be making use of the MAC table output entries, and we're going to use the show event monitor MAC and only going to grep for the remote MAC address that we are interested in. So upon running the show event monitor MAC output, we do see that there are entries being populated for this MAC address. And when we highlight a particular subsection of this output, let's see if there are any changes or any information that is useful. We do see, the remote MAC is consistently learned over the VTI, but the VTEP IP behind which this MAC is learned is changing between the VTEP IPs v1.1.1.1 and 1.1.1.2. Now, verifying the same result on the other set of VTEP, which is VTEP 1B, we're going to run the show event monitor MAC output, and we're going to grep for the same remote MAC that we are interested in. So let's copy paste the remote MAC address and see what results are we observing here. Now, upon running the show event monitor output on this set of VTEP, we see that the remote MAC is being consistently learned behind the VTI, which is the VX1 interface. However, we see the same result on this side as well, wherein the MAC address is being flapping between the VTEP IP 1.1.1.1 and 1.1.1.2. But now that we have a double confirmation on the two VTEP IPs behind which this particular MAC is flapping, it would be a good step to check the VTI status and verify the details on it. So for that, we're going to run the show interface VX1 output on both the set of VTEPs. And we see that the VTI is up and connected and having a source interface mapped to loopback 0 with a VTEP IP that of 2.2.2.2. Now, looking at the floodless source and the static VLAN to VNI mapping on both sides, it's identical. And we see that the hidden replication list is also populated. But there is one thing interesting over here. I do see that the two VTEP IPs behind which the local, this remote MAC is flapping is present on my flood list. So it would be a good step to check whether or not I have valid routes or I have the VTEP connect or IP connectivity to those remote VTEP IPs. To do that, I'm going to run the show IP route command to confirm if I have valid routes for these remote VTEP IPs. And upon running the show IP route output, I do see that I have valid routes for the VTEP IP 1.1.1.1 from the VTEP 1A and 1B. And to verify the valid routes for the other VTEP IP that I'm interested in, I'm going to run the same command as well. Now, upon running the show IP route command on both ends, I do see I have the valid routes for both the set of VTEP IPs, and to look at what is the next device connecting to our via the exit interface, I do see that the ET49/1 and 50/1 are mapping or connected towards spine 1 and spine 2, which is acting as our exit interface for the route that we checked for the remote VTEPs. So let's go ahead and look at the other details on the spine. But at this point, we did form some level of visibility into our topology diagram. And we did that, earlier we just knew that VTEP 1A and 1B was connected on the VxLAN Fabric cloud. But now we have some form of visibility that what is the next device connected to from the VTEP 1A and 1B's perspective. Now to chalk out the details and complete our topology diagram, I'll recommend you guys to download the the topology diagram that's mentioned on the chat and open that out to see how the topology unfolds and how are we able to map out the other details. Now, the basic check that we would like to perform on these spine devices would be to look at the valid routes for these remote set of VTEPs that we are interested in and see if the spine has valid routes for the remote VTEP IPs 1.1.1.1 and the 1.1.1.2. Now, upon running the show IP route command for the VTEP IP 1.1.1.1 and for the other VTEP IP that we're interested in, we see that the spine 1 has valid routes for both the set of remote VTEP IPs. Upon running the same commands on the spine 2 as well, I'm able to identify that both these set of spines are having valid routes for the two remote VTEP IPs we are interested in. And let's now check what exit interfaces what devices are mapped to the exit interface for these specific routes. So we do see that VTEP 1.1.1.2, which has an exit interface of 3/1, is pointing towards the VTEP 2B from the spine 1's perspective. And when we look at the show LLDP output again, we do see that the ET1/1, which is mapping or corresponding to the exit interface for the VTEP IP 1.1.1 on both sides, is being referenced to VTEP 2A. Similarly, the VTEP 2B, which is connected to ET3/1, is having connections or has the connections from the spine towards the VTEP 2B, which is acting as the exit interface for the VTEP IP 1.1.1.2. Well, now that we have confirmed from the spine that the two connections, or we have identical connections from the spine towards the VTEP 2A and 2B, this might confirm that there is a probability that I might be having ECMP links between the spine and these other set of VTEPs, which is VTEP 1A, VTEP 2A, and 2B. But before we jump onto any other anything, let's go ahead and look at the remote VTEPs or the VTEP 2A and 2B and confirm a few more details on those set of VTEPs. Now, looking at the show MAC address table output on the VTEP 2A and VTEP 2B, I do see that, I am learning a particular MAC address, which is corresponding to the remote MAC from the host or from the VTEP 2A, 2B's perspective, which is the host MAC of corresponding to host 1 is being learned behind the VTI. Now, since I have a valid MAC address being learned over the VTI, I'm going to check the VTI status on both the set of VTEP devices, which is the VTEP 2A and 2B. Now, upon looking at the VTI status, I do see that, the VTI or the VxLAN VAR interface is up and connected. And on the VTEP 2B side, I do see that the source interface is mapped to loopback 0, and the VTEP 2B has an active IP address or VTEP IP address, that of 1.1.1.2. On the other side, the VTEP 2A has the similar detail, but the VTEP IP on the VTEP 2A is corresponding to 1.1.1.1. And the flood list is configured manually and is referenced to CLI on both sides. Now, looking at the static VLAN to VNI mapping on both ends and the head and replication list, I do see that they are identical. and have been configured for extending the VLAN 10 over the VxLAN domain. But it would be a good time to check whether or not these two set of VTEPs are, are standalone devices or standalone VTEPs, or these two VTEPs are in MLAG. So for that, we are going to check this by using the show MLAG output on VTEP2B. And we do see that the MLAG status or the negotiation status is connected and the state is active. That means that VTEP2B is in MLAG, and looking at the system ID or the other details, it kind of confirms that the VTEP2A and 2B are in MLAG connected together. Now, drawing the information again on the VTI status on both sides, if these two VTEPs are in MLAG, they are supposed to be providing logical redundancy to the VTEP IP that is configured as per the configuration or the baseline configuration. And this config or this discrepancy that we identified using the show interface VX1 output can also be identified using the show VXLAN config sanity output. And let's continue and run this particular output on both set of VTEPs. Now, upon running the show VXLAN config sanity on both ends, I do see that the MLAG configuration check for the peer VTEP IP is failing at both ends, and I also see the routes for some of the remote VTEP IPs is not being present. But because we are still in the deployment phase, this can be ignored. Now, looking at the MLAG configuration check for the peer VTEP IP, we are going to look at the show MLAG config sanity output on both these ends as well to see if there are any other form of inconsistencies being observed in these two set of VTEPs since they are in MLAG. Now, upon running the show MLAG config sanity, I do see that there is no other discrepancy, but the peer VTEP IP check failing on the show VXLAN config sanity output gives us a confirmation that this needs to be corrected. So let's go ahead into the VTI global config mode and then go into our loopback 0 and change the loopback IP's IP address mentioned here. Let's change the IP address of the loopback 0 to that of 1.1.1.1 to keep it consistent and compliant with the VTEP2A. And let's verify if this is being reflected well now or not. Upon running the show interface VX1 output, I do see that the VTI is up and connected, and the active VTEP IP on this set of VTEPs is now identical and has been changed on the VTEP2B side. Well, now that we have confirmed that both these VTEPs are having identical VTEP IPs, it would be a good check to go back to our local VTEPs that we started our troubleshooting with and check if there are further increments in the MAC moves or not. But before we do that, let's go ahead and clear the MAC address table outputs on both the set of VTEPs by issuing the clear MAC address table output. And we're only going to be clearing out the MAC addresses being learned for VLAN 10. Now, before we check any result or check any table outputs, let's continue and run a few iterations of the curl command. And we see that the TCP connection is being formed. And let's look at the layer 2 output, which is the MAC address table output on the set of VTEPs. Now, looking at the layer 2 output or the layer 2 table output or the MAC address table output for the VLAN 10, I do see that the two MAC addresses that were being learned are correctly populated in the MAC address table output. And to see if there are any error logs or any host flaps or any other fatal errors that are being mentioned or may be occurring due to the stream of communication, whether or not they are present in my show logging output. For that, I'm going to make use of the show logging last 1 minute output. And I see that I'm not seeing any host flaps, which may indicate that the particular MAC address is being learned over two different interface, or it's being flapping between a remote VTI or a local interface as well. So with that, we kind of confirm that our remote MAC was flapping between the two VTEP IPs that we saw earlier due to a config error made on the remote VTEP side. And before we conclude this CLI session, let's go back to our slide deck and look at the summary details for this problem statement. Now, for this problem statement, we firstly confirmed that the MAC moves were being observed on these locally connected set of VTEPs, which was VTEP 1A and VTEP 1B. And the MAC moves we observed was for the host MAC or the remote host, host 2's MAC address, which was ending in with C361. We confirmed the VTEP IP behind which this MAC address was flapping using the show VxLAN address table output in conjunction with the watchdiff command. And we also confirmed a similar behavior by using or making use of the show event monitor MAC output for the remote MAC address C361. Furthermore, we also checked the VTI status on both the set of VTEPs, VTEP 1A and VTEP 1B, and then on VTEP 2A and 2B. And we identified that there was, some discrepancy, or, the VTEP IP on VTEP 2A was pointing to 1.1.1. But the VTEP IP on the VTEP 2B was corresponding to the VTEP IP 1.1.1.2. Furthermore, we also checked whether or not these two VTEPs are in MLAG, and we did that by running the show MLAG output on these VTEPs. And once we confirmed that, we were able to see that these two VTEPs were in MLAG, and they were supposed to be providing logical redundancy to the VTEP IP, which has to be identical on both ends. Now, with that, we then corrected the VTEP IP on the VTEP 2B side and confirmed that there were no other MAC moves happening on the VTEPs or the locally set of VTEPs that we started our troubleshooting with. I also mentioned the commands that can be used to verify or investigate such issues, or the useful commands on the EOS side that can be run to troubleshoot any MAC moves errors, or if you want to gather more visibility into it, and you can reference to that using the slide deck. And with that, I'll hand over the podium to my colleague Arvind. Arvind, take it away.
Thank you, Madhukar. That was truly an outstanding demo. All right. Hello, everyone. Thank you for attending this webinar. My name is Arvind, and I've been working with Arista for over 5 years. And today we're going to be looking at two specific scenarios that include VxLAN bridging, and we're going to see how we're going to go about troubleshooting and resolving those issues using CVP. For those who are new to CVP or new to Arista on the whole, or haven't attended the previous webinars, CloudVision is a network management platform that offers a unified view of the physical and virtual network infrastructure. It provides real-time visibility, automation, and analytics to help network administrators better manage their environment. CVP can be deployed on-prem using CloudVision Appliance, which is Arista's virtualization platform, or ESXi, or any other supported virtualization platform, and can also be deployed on the cloud using public cloud services such as AWS, Azure, and GCP. All right, so let's go ahead and take a look at scenario one. So scenario one is similar to what my colleague had discussed earlier. So the customer basically opens up a ticket with us stating that they're seeing an intermittent connectivity issue between host 1 and host 2, as is denoted by the red mark over here. So we know that the VTEP pairs are in an MLAG at this point, and we know that host 1 is connected to VTEP 1A, 1B, and host 2 is connected to VTEP 1A, 2A, 2B. And host 1 has the MAC address of 4A89, and host 2 has a MAC address ending with C361. As already mentioned earlier, it would be useful to download the topology diagram and keep it open, as it would help in understanding the flow as I go through the demo. All right, so let's go ahead and jump into CVP to take a look at the troubleshooting steps. All right, so in the first pane, we can basically see that we have all the devices associated with the environment onboarded. We are going to leverage the topology tab over here, which provides a graphical representation along with its connected links. So we have host 1 connected to VTEP 1A, 1B connected towards the spines, which have 4-way ECMP towards the VTEPs. We have VTEP 2A, 2B connected to host 2. We have host 1 and host 2 in VLAN 10, and they own IP 10.10.10.8 and 10.10.10.9 respectively. For this case, we're going to be leveraging the traffic flow feature, which is done by enabling sflow or ipfix on the devices. In this case, I've used sflow. I'll show you the configuration at the end of the demo. So let's go and hit flows to take a look at the traffic flows. All right, so traffic flows basically give us information about the traffic present on the links at a given time. We have the time scroller down below here, which can be used to scroll to any given time, and it will show us the flows that are present on the left. Right, since the issue is live, we're going to take a look, use the flows that we can see on the left to basically troubleshoot this specific scenario. All right, so we have a couple of UDP flows here, a couple of ICMP flows here, and a TCP flow. Right, we can use these filters here if you want to filter out the flows as per our requirements. I'm going to start off with looking at ICMP flows. All right, so we have an ICMP request that's going in from 10.8 to 10.9, which is host 1 to host 2. So we can see traffic going from the spine, going to VTEP 2.8 down to host 2. And this part doesn't seem to have an issue as the traffic is making it between host 1 and host 2. So let's go ahead and take a look at the reverse path, which would be the ICMP response. So we can see that this is from .9 to .8. So let's click on it. So we can see that traffic from host 2 is going into VTEP 2A, going to spine 2, going to VTEP 1A, and going down to host 2. So this path seems to be working fine. The only difference being that the ICMP request was hashing onto spine 1, and this is hashing onto spine 2. Right, so the ingress and egress look good there. So now let's go ahead and take a look at some of the TCP flows. Right, so we have a couple of flows out here. All right. All right, so let's click on one of them. So here we can see the traffic from host 1 making it to VTEP 1A, going to spine 1, and then it's getting black holed at VTEP 2B. So this is definitely a good data point where we can see that traffic is not making it to the host 2. So let's take a look at the next TCP flow. All right, so for this flow, we can see traffic is indeed making it to host 2. And if you look at it, it's basically taking the same path as the ICMP request. So it's not a very useful flow out here. And all we know as of now is that VTEP 2B is currently black holing the traffic, right, from the previous flow. So let's take a look at some other flows to see if we can narrow down the issue further. So we have a couple of UDP flows here as well. All right. So over here, we can see that this traffic is going to VTEP 2B, going to spine 2, and then getting black holed at VTEP 1B. So now we can say that the traffic that's egressing towards the remote VTEP from VTEP 2B is also getting black holed. Now let's see if we have something for VTEP 1A as well. All right. So if we click on this flow, so here we can see that this traffic is going from VTEP 2B to spine 2 and then getting black holed at VTEP 1A. So from this, we can basically say that traffic that's egressing from VTEP 2B towards host 2 and the remote VTEPs is kind of breaking. So we can say that our culprit currently is VTEP 2B. However, we'll also take a look at the egress links just to make sure everything looks good there. So before that, there's a feature I'd like to talk about. So we can take a look at the links and we can see that these links are color coded. The reason for that is that we have this feature enabled, which color codes the links based on their bandwidth utilization. And we have the key on the right, which denotes that. And if we hover over the links, we can also see the current bandwidth utilization on those particular links. If we want, we can go ahead and turn it off. But for this case, we're going to go ahead and keep it on and continue with our troubleshooting. All right, so let's take a deep dive into the devices. In order to do that, there are two ways. When we can click on it, select device overview, or select the device tab from the top. In this case, we're going to select device overview. All right, and then we're going to take a look at LLDP neighbors, as we want to take a look at the egress links and the interfaces. So on VTEP 2B, we can see host 2 is connected on ET5, which looks good. On VTEP 1A, we can see host 1 is connected to 85. Now we'll just take a look at the port channels because we know that these pairs are in an MLAG. So we can see that 85, pure 85 of the MLAG pair are associated port channel 100 in a connected state and in trunk mode. So now let's take a look at the remote side. We can see 85, pure 85 associated port channel 100 in a connected state and in trunk mode. So everything looks good as far as the links and the L2 connectivity is concerned. There's one other thing that we can check is what VLANs are associated port channel 100. For that, I'm going to be leveraging the snapshots filter feature. So let's scroll on top and click on snapshots. So I've created one called VLAN for this webinar. So what this does is it runs the command show interfaces trunk on the devices at a regular interval of time and throws in the output into CVP. From here, we can see that VLAN 10 is associated with port channel 100 for VTEP 2B. Now let's take a look at that on the remote end. So we can see that VLAN 10 is associated with port channel 100 over here as well. Now, snapshots is a pretty cool way of running CLI commands via CVP and having the output into CVP at regular intervals of time. And it's also, we can also use this to compare the differences between the outputs taken at different times. So in order to go ahead and configure it, we can click on provisioning, select snapshot configuration, select new snapshot from the top right. We can give it a name. We can give the EOS commands that we want to run. Here we can give in multiple commands as well, one after the other. Select the devices we want to run the commands on and the interval at which we want to capture it. All right, so next thing we're going to be looking at would be the input and output discards because we saw traffic not egressing the ports. So I'm going to leverage the dashboards feature out here. So dashboards feature is a pretty cool way of looking at multiple parameters for multiple devices in a single pane of glass. So if we have like a larger screen, we can just throw it up there and monitor the devices actively. So here we can see that we have the topology diagram. We can see the MLAG status. We can see the negotiation status, the peer link status, the number of VNIs learned, the number of port channels configured. We can also take a look at the syslogs that are actively generated. We can see if there are any events generated. And here we can see the input discards and the output discards. So if you take a look at the diagram, the ingress is on 804950 on all the VTEPs. So let's take a look at that for VTEP 1A. So VTEP 1A, we can see that 8049 and 50 don't seem to have any drops. Let's take a look at that on VTEP 1B. 1B looks good as well. Let's take a look at it on 2A. 2A looks good as well. Let's take a look at it on 2B. 2B looks good as well. So now let's take a look at output discards, which is on 85 port channel 100. 85 looks good on VTEP 1A. 85 looks good on VTEP 1B. Port channel 100 shouldn't show anything different for 1B, so that's good. VTEP 2B also looks good. So next thing we'll be looking at would be the MAC address table to see if the MAC addresses are learned in correctly. So let's click on that. Let's take a look at MAC address table for VTEP 2B. So we see that C361, we know that this MAC is behind VTEP 2A 2B. We can see that that is locally learned via port channel 100 correctly. However, we do not see a remote MAC being learned here. So it's possible that the remote MAC has either expired, right? Or there could be a decap issue. So on VTEP 1A, we can see the C361 is remotely learned. And we know that 4A89 is the local MAC on this device. Let's take a look at that on 1B as well. 4A89 locally learned and C361 is a remote MAC which is learned by VxLAN. So now let's also go and take a look at to check if all the VxLAN parameters are looking good and the mappings are looking good. So let's take a look at the VxLAN address table. All right, so here we can see for VTEP 1B, we have VLAN 10 mapping to VNI 1000. VLAN 10 mapping to VNI 1000 for 1A. For 2A, VNI 10 looks good. However, for VTEP2B, we see that there is an incorrect VNI mapping out here of 1001. And this also makes sense. The black holing at this point in time also does make sense because the traffic that's ingressing into VTEP2B would be coming in with VNI 1000, which VTEP2B isn't aware of. And if the traffic is egressing out of VTEP2B, it would be getting encapped with VNI 1001, which the remote VTEPs aren't aware of. So this would cause a decap. This would cause the devices to drop the traffic and not decap the traffic. So let's go ahead and proceed to correct this issue. So we can hit provisioning, hit config lists, select the config list that's associated with this device, hit edit. So this is the SFlow configuration that I was talking about earlier, which enables traffic flow into CVP. So let's scroll down and then go ahead and correct the VxLAN configuration. So let's change the mapping from 1001 to 1000. Let's hit save. Let's create a change control. So here we can see that the new VNI mapping is being pushed instead of the incorrect 1001. Let's go ahead and execute this change. So once this change is executed, we should see the new VLAN to VNI mapping show up for VTEP2B. And it should resume the traffic flows as well. So let's take a look at that. All right, so here we can see that now VLAN 10 maps to VNI 1000, which is the correct VNI mapping. Let's take a look at the traffic flows to see if that has begun to work. So we can see that now VTEP2B is no longer black holing the traffic towards host 2, as we saw earlier. Let's take a look at that for VTEP1A, 1B as well. So here we can see that traffic is no longer getting black holed at VTEP1B, making it to host 1. Now this traffic has a different source port, so which is why it's probably taking a different flow, and we can see that this traffic is no longer getting black holed at VTEP1A as well. Now an easier way of doing this or taking a look at this would have been via events, since it's a config issue. So we can just select VxLAN configuration error here. Currently we have it in an unacknowledged state as we just corrected the issue. We can see this event being generated, right? And it's not inactive currently as we made the change. So here, once we click on it, we can see that the VLAN to VNI mapping is not identical as what it says with its MLAG peer. And since these devices are in an MLAG, the VxLAN config sanity check would fail. If we hover over the icon over here, we can see there's a link to the Arista Community Central article that talks more about this error. So in order to go ahead and configure such events, we can hit on configure event generation. Select the VxLAN configuration error here, select the devices we want to generate an event for, select the severity and hit save. Now what's cooler is there's another easier way of doing this via topology. So if you're on the left, if you look at overlay, there's a drop down from which if you scroll down, we can take a look at this, a VxLAN option. So once we click on it, it's going to color up the VTI links, which basically tells us that VTEP2B does not have a VTI link. So right off the bat, we can say that there was probably a config issue here. And this was during the time of the issue. So once we hit live, after we corrected the issue, we can see that the VTEP2B now has VTI links. And it also does show the VNI mapping of 1000 as we can see over here. All right. So that's it as far as scenario 1 is concerned. The RCA being that there was a VLAN to VNI mismatch. And we did take a look at the steps of how we went about troubleshooting and resolving the specific issue. Now let me head back to the slides to go over and discuss scenario 2. All right, so for scenario 2, we know that the customer has opened up a ticket with us stating that they're seeing MAC moves on VTEP 1A and 1B. We know host 1 has a MAC address ending with 4A89. It's connected via port channel 100 to VTEP 1A and 1B. So our steps would be to basically identify what MAC is flapping and go about resolving that issue using CVP. So let's jump into CVP to take a look at the troubleshooting steps. All right, so as we know that VTEP 1A and 1B are seeing MAC moves, the first thing that we're going to be looking at would be the MAC address table. So let's go ahead and take a look at that for VTEP 1A. All right, so we see that C361 is the remote MAC learned via VxLAN 1 that is seeing the moves, right? So, and 4A89 is the local MAC as we know that, and is not seeing any moves. So let's take a look at that on the peer as well. Okay, so yeah, before that, we can take a look at where this particular MAC is connected using the endpoint search feature. So we can see that this MAC is connected via port channel 100 on VTEP 2A and 2B. So endpoint search is a pretty cool feature where we can search for a device using its MAC address, IP address, device name, or device ID. Now let's head back and take a look at the MAC address table of its MLAC peer, which is VTEP 1B. So we can see that the remote MAC is also seeing moves here, which would be the case. And 4A89 is not seeing any moves, which looks good. So on the remote end, which is 2A, where we're seeing C361, we can see that that's locally learned and does not see any moves here. And 4A89 is remotely learned and does not see any moves here as well for remote MACs. So let's take a look at that on VTEP 2B. So the local MAC, the remote MAC has no moves over here via VxLAN 1, and the local MAC is learned via port channel 100, and it looks good. All right, so next thing we're going to be looking at would be to identify what VTEP IPs is this flapping between. So we're going to take a look at the VxLAN address table. So we can see that on 1A, C361 is learned from VTEP 1.1.1.1, right? The port being VxLAN 1, of course, and the number of moves is 21, right, at this point. So let's go ahead and monitor this to see if it's actively flapping between what VTEPs, basically. Okay, so here we can see that it's flapping between VTEP 1111 and 1112, and we can see the number of moves increment. However, the port did not change. So let's go and monitor it again to see if it's flapping between any other VTEP. All right, so it looks like it's flapping only between 1111 and 1112. We can see the number of moves increment as well, right? So in an ideal scenario, we would be going ahead and taking a look at on the spine side to see how spine is routing to VTEP 1111 and 1112 and go about that. However, since we're using CVP, we can leverage the traffic flows feature here as well to see what flows could be possibly causing this issue. So let's go ahead and hit flows. So we can see two flows out here. So let's see what paths they are using. All right, for this flow, this is from host 2.9 to .8. It's using 50,040. So we can see that this traffic is going to VTEP 2A, then to 1B, and then down to host 1. Let's take a look at the next flow. This is also from host 2 to host 1. This has a different source port of 50,070. This time it's taking from VTEP 2B, hashing to VTEP 1A, and then down to host 1. So they're entirely using two different paths, which ideally would be causing this issue as we saw the issue live, right? So let's confirm it's indeed VTEP 2A and 2B. So let's look at the routing table on spine 1. So we can see that 1111 is routed via 1/1 and 1112 is routed via 3/1. So if you look at the LLDP neighbors, we should see this connected to VTEP 2A and 2B. Yeah, that's what we see here. So ET 1/1 is connected to VTEP 2A and 3/1 is connected to VTEP 2B. So this definitely seems to be the discrepancy between these two VTEPs. So let's go ahead and compare their configurations. So there are two ways we can do that. So we have a time configuration out here, comparison out here, which basically selects the state of a single device at two different chosen times. We can compare the states of a single device basically. And the second that we have is a device comparison, which basically compares the state of two devices at a specific time. So in this case, we want to go ahead and use that since we want to compare the configurations between VTEP 2A and 2B. So let's go ahead and hit compare. Let's select configuration. Let's search for VxLAN. Here we can see that we have the source interface as loopback 0, which looks good. We have the right VNI mapping. We have the flood VTEPs that are configured and they look consistent as well. Oh, we do see the 1112 to be part of the flood VTEP out here. So let's go ahead and compare the loopback 0 configurations, as we suspect that would be most likely the issue. So let's look at loopback 0. It has 1111 and loopback 0 over here as 1112. So yeah, definitely there seems to be a discrepancy here. And since they are in an MLAG, we should be having the same loopback IPs present over here as well. So, and we can make this change using configlets, as we saw earlier. Another easier way of doing this would be events, as we also saw earlier, via VxLAN configuration error. Currently, the event is in an active state as we haven't gone ahead and made the change. So let's click on it. We can see that there's an invalid local VTEP IP error this time, and it states that it's not matching with its peer since it's in an MLAG pair. And we can see that the VxLAN config sanity check has failed on VTEP 2B. Right? What would be cooler is if we can generate notifications for these events. In order to configure that, we can select notifications over here. And this would help us we don't need to log in into CVP to basically take a look at events every time. And we can generate this for multiple platforms such as email, messaging services such as Google Chat, Microsoft Teams, Slack, Zoom, multiple network monitoring tools as well. We can also send it to an SNMP server and also to a syslog server. All right, so in this case, I'm using email and Google Chat. So for email, I've created an SMTP host. I've configured the sender address with which I'll like to receive the email and the respective credentials. For Google Chat, we'll have to create an incoming webhook. I'll show you in a bit as how we can do that. Now let's go ahead and take a look at a sample of the email. All right, here we can see that 2 new events were generated for VTEP 2B. Right, we can see the sender address we configured. We can also see the error that was received, which was VxLAN config sanity check was failed on VTEP 2B. And it also provides other parameters and other information about VTEP 2B. So now let's go ahead and take a look at the Google Chat notifications. So over here, we can see that we have multiple notifications generated for the event seen in CVP. If we look down, we can see 2 new events were generated recently. Now, in order to configure the incoming webhook and for this feature to work, let's click on the namespace, select apps and integration. We can click on manage webhooks and we can copy this URL that we have and go ahead and paste it on chat in CVP. So this should basically go ahead and enable this feature for notification generation. So, all right, so that's it as far as scenario 2 is concerned. And the RCA for the issue was the incorrect loopback 0 VTEP IPs that were present on the MLAG pair. So now let's go back to the slides. All right. So on this slide, I have jotted down the troubleshooting steps that were taken to go about troubleshooting and resolving scenario 1. This also includes the screenshots for some of the features that we have used in CVP. The same goes for scenario 2 as well, where I've jotted down the troubleshooting steps taken to help resolve this particular issue or narrow down the issue in this case. So this should be useful if you would like to go over the slide deck instead of going over the video. And also, I've included some of the links for the features that we used in CVP during this webinar. It also includes links to the features that were used in the previous webinars. So that's it from my end. Thank you so much for tuning in and listening. And I really hope this was useful. Over to you, Loki.
Thank you, Arvind. And Madhukar, this was a really informative session. Some really great technical stuff here. We really do hope that this session was useful for everyone. Again, a recording of this session will be available on our Arista community page, along with the presentation reference material, along with all the questions which we covered and the configuration on the switches which were used in this lab setup. Our next session is scheduled on 31st May at 11 a.m. Eastern, the same time, which is going to be a deep dive into the VxLAN routing. So we definitely recommend everyone to attend that session. And also, we are actually putting a short feedback form with 3 to 4 questions in the chat window now. So please take a few minutes and provide your valuable feedback and comments about today's sessions and any topics or anything which you would like to see in our upcoming webinars. We definitely intend to use it for our future sessions. So now at this point, I'm going to keep the webinar open. If you have any questions related to today's session, please feel free to send them via the Q&A manager, and our technical leads team will be happy to answer that. So webinar is open at this point for any Q&As which are lingering from today's session. Okay, so if there are no other lingering questions, we are going to wrap this session up. Thank you, everyone. We hope you enjoyed this session as much as we enjoyed putting this together for you. So thank you so much for your time today. Goodbye.